Hello boys and girls. This is Professor Nelson from Electronics. This time, we're going to learn how LED light bulbs work, like these ones here. For example, here I have two very different LED light bulbs. This one, for example, has the integrated circuits on the same board as the LEDs. However, this one has its electronic board separate from the LEDs. But don't worry, they both work the same way. Therefore, learning how one of them works will allow us to understand how the rest of the LED light bulbs work. For that, we're going to learn, both theoretically and practically, how the circuitry of this light bulb works, or this light bulb, so that you can repair all the broken light bulbs you have at home. So, without further ado, let's continue with the video. Okay, for this example, we're going to use this light bulb. For that, we're going to take out the electronic board and then analyze how it works. Okay, here we have the electronic board. This would be the power supply for the LEDs we have here. In the case of this bulb, several LEDs are burned out. So we're not going to test it directly with the LEDs. Instead, we'll build another circuit. However, the power supply must be fine. Therefore, let's analyze it. Now, the operation of this board would be as follows. The first thing to look at is the integrated circuit's power supply. According to the datasheet, it is powered through pin 1 and pin 7 with alternating current. Alternating current can be 110, 120, or 220 volts. Now, looking at the internal structure of the integrated circuit, we can see that the alternating current inputs are connected to a diode bridge. And remember that the diode bridge converts alternating current into direct current. Since we can see that we have a negative, and we have a positive connected to pin HV or pin 6. Keep in mind that in the integrated circuit, we have a diode bridge inside the integrated circuit. That unlike other electronic boards, we have the H bridge separated. For example, on this electronic board, this would be the H bridge. So, internally, the integrated circuit converts alternating current into direct current. After that, the positive is delivered through pin 6 directly to the positive or anode of the LED diode strip. In this case, we would have a positive here. And the negative would be connected directly to the capacitor, not to the LEDs. So we have a capacitor that will have a negative and a positive terminal. That capacitor would be this one here, which is 400 volts and 2.2 microfarads. Now let's see what other components we have. Well, we have two resistors, one on pin 3, and another one on pin 4. On pin 4, we have a resistor called CS, which controls the current going to the MOSFET transistor. That is, internally, we have a transistor that controls the current or the power supply, or the voltage delivered to the LED strip. Now, how does this work? Well, it's as follows. What the MOSFET transistor does is deliver a pulse train that maintains its frequency, but the pulse width can vary. the pulse width will vary depending on the current to be delivered. For example, in this case, we have a narrower pulse width, so we will have less current delivered to the LED strip. In the case of the second example, we would have more current delivered to the LED strip. Now, who controls that current delivered to the LEDs? Well, it's the resistor on pin 4. This resistor controls that current because a voltage will fall across it. That is, we will have a voltage drop across the resistor at pin 4. That voltage will be compared with this constant of 0.373 volts, which in this case is compared by an operational amplifier, which in turn will control the MOSFET transistor. That is, what is done through pin CS is to send the pulse train, whose pulse width will depend on the value of the resistor. Now, in the case of the LEDs, we won't have this signal. Instead, we'll have a continuous or constant signal. In this case, we'll have a lower voltage. And in this case, a higher voltage. The voltage will be displayed continuously thanks to the capacitor we have here. That is, we won't have this pulse train on the LEDs. Instead, it will remain as a constant DC signal thanks to the capacitor. Now, how do we calculate the resistance value? Well, that will depend on this formula. This formula is from the integrated circuits data sheet, where it tells us to calculate the peak current, and then the current falling on the LEDs. The peak current is a function of this constant, which is the current falling on the comparator we just saw. Therefore, in this case, the peak current will be equal to 0.373 divided by the resistance that this integrated circuit or electronic board currently has. In this case, it would be 1.5 ohms. That would be the resistance at pin 4. So, we have 1.5 ohms. So we'll have a current of 0.248 amps, or 248 milliamps. The current to the LEDs will be half that. In this case, it would be 124 milliamps. This means that 124 milliamps will be delivered to the LEDs. This is very important because you can modify the output current of the integrated circuit. This way, you can extend the lifespan of your LED bulbs, preventing the LEDs from overheating. Therefore, by changing the value of the resistor we have here, you can increase or decrease the output current. Simply use the formula, and based on this, you will be able to obtain an appropriate output current for your LED diode strip. Now for the voltage. The voltage will be adjusted based on the number of LEDs we have connected. If we have several LEDs, the voltage will increase. And if we have fewer LEDs, the voltage will decrease. All of this with a current controlled by the resistor on pin 4. However, we don't have a resistor on pin 3. Since you can see there is no resistor here, we can't use it to protect our electronic board. Since pin 3 should have an overvoltage protection resistor, we don't have one built in, so we can't use it. Next, we'll test the OVP on other types of bulbs if they have that feature activated. Okay, this is how the circuit or power supply for an LED light bulb works. The rest of the bulbs would work similarly. Now that we've covered the theory, let's move on to the practical part. Measure both the voltage and current delivered to the LED strip. Now for the practical part. We'll power our electronic board with 220 volts alternating current. This will allow us to see the output voltage when one of the LEDs is burned out. To do this, we will place our multimeter in direct current at a voltage greater than 300 volts. We'll connect negative to negative and positive to positive. We can see that we have 311 volts at the output when we don't connect any LEDs. This means that when we have 220 volts input, this alternating current voltage is converted into 310 volts direct current. This voltage exits through pin 5 to the LEDs when one of the LEDs is damaged. Therefore, we must be very careful when handling this when one of the LEDs is damaged. Now we're going to determine and confirm the output voltage, which adapts to the number of LEDs we install. We're going to do this by connecting several Zener diodes instead of the LEDs. We're going to use 4 Zener diodes. We're going to connect 4 15-volt, 1-watt diodes in series instead of the LEDs. To do this, you must de-energize the circuit board and connect the Zener diodes. The diodes must be connected in reverse. This means that the cathode must point toward the positive pole, and the anode has to go toward negative. There you can see that I have the cathode connected to positive, and the anode connected to negative. Pay close attention to the multimeter display. We have 65 volts, which is the sum of 15 plus 15 plus 15 and plus 15, which would give us 60 volts, which is shown on the multimeter. This means that the output voltage will adapt according to the number of diodes we connect. For example, we're going to connect only 2 diodes. And it should deliver approximately 30 volts. And we have 30 volts. We don't leave it on for too long because the power in the Zener diode will be 2 watts. In this case, we're using 1-watt Zener diodes. Remember that the current passing through the circuit is 124 milliamps. Multiplied by 15 volts, this gives us 2 watts, which could damage the Zener diode. Now, let's confirm the current passing through, which should be 124 milliamps. To do this, we set our multimeter to direct current at 200 milliamps or a larger scale. Turn on the circuit and pay attention to the display. There we have 124 milliamps using only 2 Zener diodes. Now, let's connect the other 2 diodes and confirm that the current remains the same. Okay, now we're working with 4 diodes. Let's see if the current remains the same. We energize. And we have 120 milliamps. We have a current very close to the calculated one, so we can see that the integrated circuit is doing its job correctly. Now we're going to modify the resistor value to reduce the current delivered to the LEDs. So let's do that so we can keep the Zener diodes energized for much longer without damaging them. So let's do that. Okay, for the modification, we're going to replace this 1.5 ohm resistor with a higher value resistor to reduce the current. What value will the resistor be? Well, it's going to be 4.7 ohms, so we have a peak current of 80 milliamps. And the current through the LEDs is 40 milliamps. We'd be going from 124 milliamps to 40 milliamps, which will allow us to maintain the Zener diodes for much longer. The resistance they can occupy can be of the SMD type, like this resistor, or like this resistor, but it has to be 4.7 ohms. Now let's modify our electronic board. Alright, guys, we've modified our electronic board. There you can see that we have the 4.7 ohm resistor, which will limit a maximum output current of up to 40 milliamps. Now let's confirm that maximum output current. To measure the current, we will put our multimeter in direct current, and we will bridge the circuit. Energize the electronic board. There we have 40 milliamps. Now let's use only 2 diodes and see if the current stays the same. We have approximately 40 milliamps. That means the modification we made to the circuit board is working correctly. Now let's measure the voltage drop across the Zener diodes. We change our multimeter to DC voltage, in this case setting it to 200 volts. We energize the circuit board. There we have 60 volts. Now let's test with two Zener diodes. There we have 30 volts. And that way our circuit board should be working correctly. Therefore, the modifications we just made are working correctly. So, this way you can modify the output current for the LEDs you're using. And this way you'll protect the LEDs in your light bulb and, at the same time, you'll be able to repair any faulty bulbs. Very well, this concludes the video. Now don't forget that if you like the video, a like helps the channel a lot. See you in the next video. Bye-bye.